Okay, so time to get started. Real quick, before we get into the math, I have a question. Somebody left a very nice seeming Microsoft Surface up on the front podium there yesterday, and I kind of only barely noticed. So anyway, I forgot to ask last time if this belonged to anybody. Now, I did notice it before class started, so I don't think it's one of y'all's, but I just thought I'd ask. If anyone has been missing a Surface, anyway, there it is. I'll take it to the lost and found after class. Okay, so here's where we left off. We were talking about linear transformations. Recall we have a new definition here. A linear transformation is a function from a vector space to another vector space that satisfies the linearity property, right? And we saw some ways that this might show up in language, right? And some examples, and we're just going to pick it up from there. Yeah, there was an example. Okay. So, all right. So, one thing I just want to sort of warn everyone about, it's tempting to look at linear transformations, and we're going to do a lot of things with linear transformations and get a little bit too sort of presumptuous about it and think, well, this is Math 216, so every function I encounter must be a linear transformation. So sort of obviously not true. Nevertheless, I think it's good to make that conspicuously clear. So here we go. This function, not a linear transformation. Do y'all have a question in the back? Can I help y'all? Is there a question back there? No. Okay. Is this a linear transformation? Well, if it were, these two things would have to be equal. Now, this is just sort of an easy, for example. A linear transformation would have to satisfy that property, but it clearly doesn't. I mean, take these numbers, plug in, you get 4. And you take these numbers and plug in, and don't forget to multiply by 2, and you don't get 4. So, not equal, and therefore not a linear transformation. It's sort of obvious that it's not a linear transformation, right? You see a quadratic term right there. Anyway. Okay, I want to show you all some more examples of linear transformations. This first one's a little bit weird. This first one seems weird because it's our first one, but our first sort of non-Euclidean one. But nevertheless, this is a linear transformation. Namely, here it is, the act of differentiation. So, the act of differentiation, if you give me a differentiable function, I can differentiate it and out comes, some function. Right? Now, we've discussed previously that is a subspace of F and therefore a vector space. Of course, we already know that F is a vector space, so the domain and target of this function are both vector spaces, and this function takes something from the domain and gives me something in the target. Okay. Now, a lot of students look at this and think, wait a minute, you're telling me derivatives are linear. But this is obviously false because I've seen lots of derivatives in my day. And so, for example, this f prime, I mean, what if f is sine x, then f prime is cosine x, and cosine x is obviously not linear. I mean, it's not even close to linear. Right? So this weirds a lot of students out, and what I want to point out is that you've got to be very, very careful in identifying what exactly are you saying is linear. Right? So I am not saying that this is linear. That's not the assertion. The assertion is that this is linear. Right? So D is a function from a vector space of functions to another vector space of functions. This other thing over here, f prime, that's a function from R1 to R1. Not the same thing, right? So we're not saying that that's linear. Certainly not. It's obviously not linear, right? We're saying that this is linear. Okay, and you can see that in how the proof works out. I mean, the way we confirm that this is linear is we look at, carefully, by the way, look at this D function, right? Note what its domain is. Its domain is that vector space. We do a linear combination of inputs. Well, from the domain, of course, that's where inputs live. So we're doing a linear combination in that vector space. Seeing what your domain is for your candidate linear transformation tells you what kinds of things you should be taking linear combinations of to check the linearity. And in order to check that linearity, of course, we need for D of a linear combination of inputs to give us that same linear combination of outputs. A little calculation confirms it. Let me walk you through that calculation now, just to make sure we have the details right. This first step is just the definition of D. Right? This second step is Calc 1. Right? Flashback to Calc 1. If you have a derivative of a sum of two functions, you already know from Calc 1 that is the sum of individual derivatives. And if you have a derivative of a scalar times something, you know that scalar factors out. So sort of a two Calc 1 steps gets you to there. And then, lastly, that, again, is just the definition of D, and likewise, that is the definition of D. Okay. All right, so that's how that argument goes. Let me hit the pause button for a question here, if anybody has any questions. Anybody? Is everybody happy? Okay. All right, so a common mistake that we see a lot on exams is, we'll ask, we'll give this to, as an exam question and say, okay, show that this is a linear transformation. And a common thing for students to do is to, not really knowing what's going on or how to start, or really being very comfortable with the ideas. A student might start looking at, f prime of C1x1 plus C2x2. And a student who writes this and then, goes on and does other things and whatever they conclude, this student is fundamentally misunderstanding what we're saying is linear, like I was talking about before. They're taking a linear combination of values of x. Values of x are in the domain of f prime, right? Which is not what we're saying is linear. The linear combination should be of things that are in the domain of the actual candidate linear transformation. We should be taking a linear combination of differentiable functions, not a linear combination of real numbers. Okay. All right. So, that's a good exercise to think through, I think. Now I've got a bunch of other examples I want to show you all of linear transformations. Just going to walk through them. Some of these I'm going to leave as exercises for y'all to do on your own. At least one of them I'm going to do out in gory detail, right? Kind of like this. But some of these you will need to check on your own. For example, this one here. Going back to chapter 1, you may recall, and I commented on this last time as well, but if you have a matrix, you can view it as a function. And we did a lot of stuff back in chapter 1, said, interpret your matrix as a function. And we talked last time about how, and that's a linear transformation. So this is something you can directly confirm. And the way you directly confirm this, by the way, notice my domain is Rn. I'll be taking linear combinations of elements of that domain, namely Rn, namely vectors like that, right? And so what you need to do is take T of a linear combination of vectors, input vectors, and evaluate, see what you get. Use the definition that you're given of T. Use algebra of matrices that you already know. And you just need to make sure that what you get is C1 T of x1 plus C2 T of x2. Okay. All right. Does that make sense to everybody? Again, I'm going to leave blanks in here for y'all to fill in. Algebra of matrices is going to play a large role there. Okay. All right. Moving along. Next one. Here's another weird looking one. This thing here. Let's see here. Yeah. That scary looking thing is a linear transformation. Now again, suitably interpreted, right? I am not saying that integrals in general, whatever, if you compute an integral, that's somehow a linear result or something. That's not what we're saying at all, right? I'm saying that this action here, the act of taking a function, a C infinity function, arbitrarily, the act of taking that C infinity function and of doing an integral of it, that process of integration on an interval from A to B, that's what we're saying is linear. We're saying this is linear. Okay, I'm going to write out this proof in gory detail now. I just want everyone to, see the process. Our domain we just discussed is this. We're going to be looking at functions that I'll be computing integrals of. Those functions, that's the kind of thing that I'll be taking linear combinations of. So specifically, I'm going to need some space. Let me zoom in over here, get myself some space to work. I'm going to need to compute S of C1 F1 plus C2 F2. And I'm going to need to compute that, and I'd better end up with, at the end, C1 S of F1 plus C2 S of F2. That's what it would mean for this to be a linear transformation. Again, S, right? Not the integral itself, but the act of integration. Okay, so that's our hope. So let's see if that's going to work out, and not to be presumptuous, let me slide this over here out of the way. Okay, so now let's start evaluating. By definition, S is the integral from A to B of that thing. That function of x dx, that's just definition. To be as careful as I can be, let me take a step here to recognize what it means to take a linear combination of functions. And reminder, back in chapter 2, we talked about what does it mean to add two functions. Thinking of functions as being vectors in a vector space, what it means to add two functions is you add their output values. And likewise, what does it mean to multiply a function by a scalar? It means multiply the output values by that scalar. So from chapter 2, I can rewrite this as C1 F1 of x plus C2 F2 of x. Yeah? Okay. Let's see here. Now, at this point, I'm going to invoke some single variable calculus results. We already know from Calc 1, Calc 2, I guess it is, somewhere along in there, that an integral of a sum is a sum of two separate integrals. So I'm going to rewrite this as integral from A to B of C1 F1 of x dx plus integral C2 F2 of x. That's just Calc 2. Let's see, I also know from Calc 2 that I can factor out constants outside of integrals. Takes a little bit of time to write this sort of thing down, unfortunately. And did we get the desired result? Well, yeah, look at this. We did. That's S of F1. And that is S of F2. Oh, there we go. And now let me zoom out so that we can see the whole thing. Hopefully on the, yeah, okay. Yeah. Okay. So there's the proof. That's the proof of that is linear. Okay, so like I say, gory detail, there it is. Notice that all I did is write down with fingers crossed my hope that linear combinations in result in linear combinations out, and then I just started writing down true facts that I know, capitalizing on what I know about the operations in question, and, well, it worked out. Okay, so the rest of these I'm going to pretty much leave as exercises for y'all. It's going to be pretty much the same process. Let me walk you through what the exercises are that you're going to need to do. Here's a function. Looks a lot like item number 3 there, but it's a little different. There is a fixed continuous function called g that is sitting inside of the integrand there. That was not part of item 3 above. And it looks nonlinear. Again, at a glance, you look at what's going on here. Oh my gosh, we're multiplying 2 functions. Isn't that going to be probably like quadratic or something? And again, keep in mind, that's not the thing we're talking about. I'm not saying the integrand is continuous. I'm not saying the antiderivative is continuous. I'm saying that the act of doing this to an f, that action, is linear. Linear. Sorry. Okay. All right. So exercise. The way you're going to prove this is not that different from this. Slight edit. And like I say, I think it's a good exercise for y'all to do that on your own. Okay. Side note, just in case you're curious, this particular construction is actually a really useful construction. This is not manufactured. This is a very useful construction in statistics and probability, in physics, and various other places. It's actually a pretty powerful construction in a lot of ways. Okay, y'all see that in future classes. Okay, here's another one. This one's actually much easier. A lot less algebra that goes into this one. This is a matter of writing it down carefully, but a strange formula here. If you give me a C infinity function, I'm going to do a certain process that will result in a real number. And the process is, what I'm going to do to your function that you give me to get the resulting real number is I'm going to just plug in 0 into your function. Right. So you give me a function, I gave you a number, and here's how I'm going to do it. Right, so we have a definition there of this function. A side note, this is, depending on the context, sometimes this is called the Dirac distribution or the Dirac measure. It's also, y'all will hear this in some cases referred to as the Dirac delta function. And there's a kind of a point of view there. There are some subtle discussions to be had about how to interpret this in the way that people intend when they say Dirac delta function. If anyone's curious about there, I really enjoy that conversation. It's very interesting, but it's just that it takes about 15 minutes. So if you're curious, come to office hours. I'll be happy to show you. Otherwise, you'll see that in Math 353, and it's not required in this course. Okay, nevertheless, what you can do at this stage is prove that is a linear transformation. Again, you're just going to take a linear combination of inputs that look like this, C infinity functions, and show that the action of plugging in is linear. Okay, details for y'all. Likewise, if you plug in something other than 0, still linear. If you take various derivatives in advance, still linear. And again, I emphasize, I'm not saying that's linear. Certainly not. Right? Not saying that's linear. I'm saying that the process of doing that to some test function f, that's the thing that's linear. Okay. So, another good exercise. Take a few minutes to do that. By the way, of course, on all of these, if you get stuck, if you have trouble, you can ask me in office hours. Be good questions to ask in discussion section, help room, not help room, excuse me, office hours for both your TA and and all the other TAs. So feel free to come get help if you get stuck. Okay. And then here's a last quick one. We've already considered these linear differential equations, and now per something we discussed last time, right? There's that word linear. I didn't say linear transformation. I just said, this is a linear differential equation, and I hope you'll follow the two-step advice that I gave last time, which was when you see that word linear, identify the function. Somewhere in this discussion there is a function. There's the function that is being described. The action of doing, whatever the left-hand side of the differential equation is, the action of taking a y and taking various derivatives of it and multiplying by coefficient functions, all of that stuff. That total process is linear. We actually proved this back in chapter 4. We just didn't say the word linear transformation. Okay, but this is a linear transformation from Cn to C0. And you can look back to the first page of the lecture notes on chapter 4 to see those details. Okay, yes?
So you mean the process of finding the general solution itself is a linear transformation?
Well, no, what I'm saying here is when I say that this is linear, what I'm saying is that the act of taking a function y and doing something to it that we hope will end up being g, that process of turning a y into something we hope turns out with a certain result, that process of what the left-hand side of the equation does, that's what we're saying is linear. Yeah. Does that make sense? Anybody else? Okay. So there's some facts about linear transformations and some definitions, a little bit of groundwork that we have to get done. So the next 15 or 20 minutes here is going to be a bunch of little minor items that need to get done. This first one I think is really important. It's a theorem that I need to state and prove and give you an example. Here's what the theorem says. And keep in mind, if you're looking at a linear transformation, right? Linear transformations have a domain that is a vector space. And the first thing that this theorem says is, suppose you have a basis for that domain, right? Collection of vectors, definition of a basis, it's got to be independent, it's got to span the whole domain. Okay. And suppose you know the images of those basis vectors. Now, images, let me just remind you, an image says what comes out of the function. So, in other words, looking at a handful of vectors in this domain, if I know what t does to a handful of vectors in that domain, that's the premise of this theorem, then the result is that completely determines all the values of the linear transformation. This is an outrageous conclusion. That's saying, if I know what t does to a very short list of vectors in its domain, then I know what t does to all of the others. How could this be? There's a whole vector space here. There's infinitely many vectors in this vector space, right? For example, let's suppose V is three-dimensional space, right? There's infinitely many vectors in three-dimensional space, and I'm saying that if you tell me what t does to just these three right here, just those three, tell me just that little bit of information about t, and I'll tell you the rest of the formula for the remaining infinitely many vectors in the domain. It seems absolutely outrageous. I'm going to prove it, and then I'm going to come back and tell you why this is important. Here we go. Let's suppose that our basis for the domain consists of these vectors v1 through vk. Right? And keep in mind, I know what t is for those vectors. I know t of v1, t of v2, etc. Okay. So now let's just take any other vector, whatever. Any other vector in the domain. Well, by assumption, these vectors are a basis, and a basis has the wonderful feature that no matter what other vector you might be considering, that vector must be a linear combination of those basis vectors. That's one of the nice things about a basis. Okay. The thing I want to compute now, keep in mind, I'm hoping to be able to decide what does the linear transformation do to this arbitrary vector that I pulled out of nowhere? I need to be able to compute t of v, in other words. Well, v is that linear combination. Right? So t of v is t of that linear combination. T of a linear combination. T is a linear transformation. I can cite linearity. A linear combination going in gives you that same linear combination of the outputs. That's just using the linearity property. And keep in mind, by assumption, I know the images of the basis vectors. So I know T of all of these, V1 through VK. So this thing here, I know what that is. Et cetera, et cetera. This T of VK, I know what that is. Right? So whatever vector you give me, any vector in the vector space, if I know the orange images, well, I can figure out what these coefficients are through Chapter 1 methods. Now I know the yellow coefficients, I know the orange images, and therefore I know the value of the linear transformation by that formula. So there we go. I mean, it almost seems like a magic trick. Like, how could this possibly be? I've got a deck of cards here, and I'm going to look at the top 3 cards. And from knowing the top 3 cards, I'm going to tell you all the rest of the cards. That'd be a good trick, right? That's kind of like what's happening here. Okay. All right. For example, now again, let's just see it work. Let's suppose that I know I've got a linear transformation. I forgot to write that down. So this is, let's suppose that's given to be a linear transformation. And let's suppose I know the image of 1, 1, let's say, and I know the image of 1, 2. Let's pretend. Notice that 1, 1 and 1, 2 form a basis. Independent pair of vectors in a 2-dimensional domain. It's a basis for that 2-dimensional space. And I claim that now I know everything about this linear transformation. I've only got 2 values given, but I can tell you all the other values. For example, if you want to know what is T of 3, 4, how am I going to compute T of 3, 4? Well, look, 3, 4 is a certain linear combination of those basis vectors. Then I just invoke linearity, as we discussed. There I am invoking linearity. I know these output images. Those were given. And therefore, knowing these coefficients allows me to get what I need. T of 3, 4 is that. It's a neat process. Questions? Yes?
So, in the previous example,
yep.
Are you saying that the images of...
You say the previous example.
in the proof.
In the proof, yeah, okay.
Are you saying that the images were just a linear combinations of the vectors and bases?
I mean, that's if I heard you correctly, the image that we're trying to find, yeah, the point is that it is, by just as an immediate consequence of linearity itself, it is a linear combination of the given images. Every image is a linear combination of the given images because every input vector is a linear combination of the known basis vectors. Yeah. Right. Okay, yeah. Image means output from the function. So the image of a vector means what comes out of the function when you plug that vector into the function. Yeah. Right. Okay, so let me tell you why this is important, why this is useful, or a point of view on that. I mean, we're going to do a lot with this. It's going to be sort of subtext in a lot of things that we're going to do. The way I like to think about this is what this tells you is how few linear transformations there are. There's very, very few linear transformations. If you prescribe so much as a couple of conditions, well, I want my function to evaluate like this at that point, and like this at that point, and like that at that point. Couple of constraints, and there's only one possibility left for what that function could possibly be, because there are so few linear transformations. Another way to think of that is how much it says when you say that something is a linear transformation. That says so much about the function. It's such a huge piece of information that knowing just a sprinkling of additional information allows me to know everything about the function. So anyway, I think this really underscores that fact. Okay, next thing. A definition. I'm going to define something called the kernel of a linear transformation. It's really a pretty simple idea. The kernel of a linear transformation is just the collection of input vectors whose output is 0. That's it. The set of inputs whose output is 0. The set of inputs that, when you put them into the function, they land on 0. And it's a pretty familiar idea. Let me connect the dots to what you're probably thinking about. Think about this function here. Again, we've done a lot with this function, namely the function that is defined by a matrix. Right? And, well, for this function, the kernel is just a null space, right? The set of vectors that when you multiply by a given matrix, it gives you 0. That's the null space. Or said differently, it's the set of homogeneous solutions, as we would have said it back in chapter 1. So we have now kind of 3 different points of view on the same idea. In chapter 1, we said set of homogeneous solutions. In chapter 2, we said null space. And now here in chapter 5, we're saying kernel. Right? So, that seems a little silly to have 3 different points of view on the same thing, but yet here we are. I do want to point out that these are not exactly the same words. You can't say null space interchangeably with kernel, because very importantly, null space only applies to matrices. You can talk about the null space of a matrix. Period. Just matrices. Right? Kernel, this notion, kernel, is for any linear transformation. And there are plenty of linear transformations that are not matrices. So, okay. All right. A geometric example. Let's look at this matrix here. Defines a linear transformation T. And I claim that this function, a quick appeal, what this does is this just projects points down into the XY plane in 3 space. It's a pretty easy pitch. If I were to say T of XYZ, then 1, 1, zeros everywhere else, times XYZ, and it gives me XY 0. Right? Pretty easy to see what that means. This says if you take a point, XYZ, the action of this linear transformation is to give me, well, here it is, x comma y comma 0. That is the point in the xy plane sitting directly below or directly above or below that input point. Okay, so said differently, this function, this linear transformation is the, squish it down into the xy plane function. All right, so easy pitch, I think, that this sort of squishing function, the kernel is the collection of points that squish down to 0, and that's the z-axis. The z-axis is exactly the collection of points that when you throw away their z-coordinate, you get pushed onto the origin. Okay. All right. Okay, another quick example, and this is just to kind of connect some dots. We already know that this is a linear transformation. We made that observation recently, and let me just point out then that the kernel of that linear transformation kernel says I'm looking for when the linear transformation equals 0, in fact, then that's this homogeneous differential equation. So we didn't think about it in those terms back in chapter 4 when we were looking at these kinds of differential equations. We thought of it as, well, this is a differential equation. We're solving a homogeneous differential equation. But just, again, connecting the dots here in chapter 5, we can choose to view this from a different linear algebra point of view. We're looking for a kernel of a certain linear transformation. Okay. All right. So, like I say, just to connect the dots. Okay, another definition I've got to make, image of a linear transformation. We've talked about that already, actually. We talked about, what is the image of a function, and the image of a function is the collection of points in the target that are actual outputs from the function, that come from actual inputs into the function, right? So again, we distinguish between the target, which is just, a space where the outputs have to land. We distinguish that from the image, which is the actual outputs themselves. Okay. All right. So a neat connection I want to make regarding that, again, in the context of that linear transformation there, our old friend from chapter 1, thinking of matrices as functions that we now know are linear transformations. I'll remind you, here, let me circle that like this. I'll remind you that the way you multiply a matrix times a vector is by taking a linear combination of the column vectors, right? So this is kind of a section 1.2 fact. I made the promise that I was going to come up over and over again in this class, and it's come up several times, and here we are again, right? So please don't restrict yourself to the point of view on matrix vector multiplication based on dot products. That's probably the least useful of these several points of view that I know about how to multiply a matrix times a vector. Okay, with that noted, well, what's the image of this linear transformation? Well, the image is the collection of all outputs. Therefore, it's the collection of all linear combinations. We have a word for the collection of all linear combinations. That's span. And the span of the columns is the column space. So there's another chapter 5 to chapter 2 connection. Kind of an sort of analogous to the kernel being the null space. Kind of analogous to that is the image is the column space. You might have wondered back in chapter 2, who cares about the column space? When is that going to matter at all? In what sense is it at all natural to be interested in the span of the columns of a matrix? Why would that matter at all? We have an answer to that question now. The reason it matters to think about the span of the columns of a matrix is because that span is this very natural thing called an image of this very natural function representing the matrix. So that's a really natural construction. Take a matrix, think of it as a function. Let it do what matrices do. Multiply by stuff. Right? Nothing arbitrary and weird about that. That's a very natural thing to want to do. Looking at what comes out is a very natural thing to want to do. So column spaces are very natural things. All right. Okay. Looking back at that function on the previous page, let me remind you we were looking at this function here. With that formula, it's the squishing things down to the xy plane. For that function, let's ask what's the image, and is it sort of visibly relatable? Well, I think it's a pretty easy appeal. That the image, the result of taking three-dimensional space and squishing it down like this, what's the final product of squishing everything down to the xy plane? Well, the xy plane is the image. And as this predicts, the xy plane is the span of the column vectors. Those column vectors, recall, 1, 0, 0, 0, 1, 0, 0, 0, 0. And it's easily confirmed that the span of those column vectors is the xy plane. Okay. All right. Okay, couple exercises for y'all on this. Given a linear transformation, the kernel, I wanted that in a different color. The kernel of a linear transformation is always a subspace of the domain. Nice little exercise. Couple of things that are going on here. One is, this is a flashback to chapter 2. We're trying to prove something's a subspace. Got to remember how to prove something's a subspace, right? And of course, the connection to chapter 5, we're talking about this newly introduced item, this kernel. Related example, the image of that linear transformation is a subspace of the target. Again, chapter 5, chapter 2 connection. So a quick hint, y'all have actually already seen some proofs that are mild tweaks of these two proofs that I want y'all to fill in the blanks on. So where have you seen a proof that a kernel is a subspace? Well, I haven't really shown you that exactly, but I did show you, look in the lecture notes way back to chapter 2. I did show you that the set of homogeneous solutions for a matrix was a subspace. Right? So structurally, that proof is going to look a lot like what you're going to be aiming for here. Likewise, I haven't shown you anything about an image being a subspace. Well, of course not. We just defined this, right? But I have showed you, and again, flashback to the notes. Look back in the chapter 2 notes. I've got a proof. Maybe I left this as an exercise for y'all. But one way or the other, y'all will see back in chapter 2 somewhere that a span of a collection of vectors is a subspace. And recall, the image is a span of a collection of vectors. At least in this case. And anyway, structurally, that proof is going to go a lot like this one. Okay, so there are some details. I mean, they're not exactly the same proofs as their chapter 2 counterparts, but they are structurally analogous. And I want to encourage y'all to try both of these proofs. I think they're good practice problems. Okay. Alrighty. Okay. Another neat fact, the book proves this right here. I'm not going to prove this result now. I'm going to prove it later. I'm going to all but prove it now. But the final piece in the puzzle won't actually get pushed in until section 5.3. There's some details that we have to pound out. But anyway, here's the result that I'm claiming. If you have a finite dimensional vector space, very important, if you have a finite dimensional vector space, and if you have a function that is a linear transformation defined on that finite dimensional vector space, then super awesome result is that the dimension of the kernel plus the dimension of the image is equal to the dimension of the domain. Very surprising that these things would be related. Let me remind you, the kernel, after all, lives inside of the domain. The image, again, recall, doesn't. It lives inside of the target. So it's very weird, I think, that these two things, the kernel and the image, that live in completely different places, are nevertheless related in the sense that their dimensions always add up to the same thing. So that's pretty weird. Anyway. The book, like I say, the book proves this fact. The book's proof has a lot of tedium in it, and it's what I would call unnecessary tedium. There's a much slicker way to do it. I'm going to show you the slick way to do it, and if you want to look and see the book's clunky, tedious way to do it, I mean, you can, right? But I think you'll like my way better. And that is, now I'm going to put an asterisk on this. I do have to make one assumption that I will prove later. And that is that every linear transformation defined on a finite dimensional domain, which we are, right? Finite dimensional domain, that's an important constraint. can be written as a matrix. And I want to remind you, just a few minutes ago, I said, hey, not every linear transformation is a matrix. There's a bunch of linear transformations that aren't matrices. We saw some, right? We defined a linear transformation from C infinity to R1. That's an infinite dimensional domain, right? And it cannot be written as a matrix. But I'm not saying that every linear transformation can be written as a matrix. I'm saying the ones that have finite dimensional domains, they can be written as matrices. All of them. Not ready to prove that fact yet. That's going to be a result from section 5.3. So I will come back to that in, when we get to the appropriate point in section 5.3. For the moment, I'm just going to say, trust me on this for the moment. But look what we can do with this result, though. If we assume that our linear transformation can be written as a matrix, well, it's all over pretty much, because we've already made the observation that for these kinds of functions, the kernel is the null space. And the image is the column space. And so therefore, this thing that we're trying to prove is equivalent to this thing that we proved a long time ago, right? We proved this back in chapter 2. This is an easy observation about pivots and where they are, and the dimension of the null space is the number of columns with no pivot. The dimension of the column space is the number of columns with a pivot. Altogether, that adds up to the number of columns. Right? So, easy proof of this fact. And as long as I assume my linear transformation can be written as a matrix, I therefore am already done with that fact. I think that's lovely. Now, again, I owe you a demonstration that every linear transformation on a finite dimensional domain can be written as a matrix, and that'll come along. Okay. There's a neat special case of this that comes from an idea that in theory y'all have seen before. In practice, in my experience teaching Math 216, I know that those of you who have seen the following idea, many of you have forgotten it. So I accept this, and it's a little too bad. But anyway, there's an idea from single variable calculus that very often gets a little too swept under the rug, and that is, what does it mean for a function to be bijective? Or another way to say this is 1-to-1 and on-to. So anyway, you might have a faint memory at some point in calculus when you're trying to define what the inverse of a function is. You need for the function to be 1-to-1 and on-to. And so just a reminder, again, I accept and realize that a lot of y'all have kind of forgotten about that. But if you have a domain and a target, and if just for figurative purposes, let's suppose those are the elements of the domain, and these are the elements of the target. A bijective 1-to-1 and on-to function is a function where every element of the target has exactly one image from the domain. Right, so, for example, this function here is bijective 1-to-1 and on-to, because for every output there is exactly one, no more, no less, exactly one input whose image is that. Right, so a function that is not 1-to-1 and on-to, for example, would be a function like this. That function is not 1-to-1 and on-to. For one thing, problem, nothing lands on that poor lonely output value. Right? It's not the image of anything. So that's violates the rule. Right? And the other problem is this output. That's the image of two different inputs. And again, to be 1-to-1 and on-to, I need for every output to have exactly, no more, no less, exactly one, and two is not exactly one. Okay, so we're at a time. So why don't I draw a line here, and we'll prove this theorem on Wednesday. See y'all later.